morning, everyone. Thank you for being here. Today, we are going to talk about a very popular topic, agents, and how agents can help microservices architecture to have a more optimal behavior within our orchestrated framework. My name is Haghighi. I'm a senior director and a senior distinguished engineer at Discover Capital One. I'm joined by my colleague, Prasanth Pari, principal engineer, one of our top engineers in our team, focused on testing and quality engineering. So for the first part, we are going to focus on microservices and agents and how they basically can be great matches. And then we're going to go into some details about the failure scenarios and how agents can actually fail. And the sort of outcome out of those failures can be quite catastrophic. And then there's some new challenges in the agentic systems and how we can actually navigate those challenges and find ways to actually optimize their operational paradigm within our framework. And then obviously, control as code. How can we actually introduce some sort of constraint, some sort of boundaries around our agents to make sure that they behave exactly how we expect them to behave? Some of the policy actions and some of the boundary changes, those boundary changes are about the agents and how they can actually get out of their constraints and do different things and act in a way that we don't actually expect them to act. And we are going to talk about those different sort of scenarios where those boundary changes are going to happen within our microservices framework. Some of the testing strategies, how can you actually put together a number of rules and guidelines to test your agents, not only in your testing and staging, but also in production. How can we actually be ready for production environments with your agents? And then the architecture integrity at the end. We've got a lot of slides to go through, but we're going to make it as practical and again, based on real-world scenarios, so it would be quite useful to you if you are going to take that knowledge back to your companies, to your startups. You know exactly what to do. And these are some of the most sort of practical scenarios where we've actually seen agents in operation in big applications, sizable teams. So with microservices, and I'm sure most of you are completely familiar with microservices, but we're just going to give a quick introduction. There are a lot of pros to microservices. When we break down our applications into multiple pieces based on the business logics and the business capabilities, we get a lot of advantages out of them. One is that they're basically designed in a way that each one of these microservices is responsible for a certain business capability. And then that gives you a lot of flexibility to design your service in a way you want without any sort of reliance on other services, and that basically can expedite your development journey. And then that independent development helps different teams to evolve and work on different services independently. And at the same time, the deployment can be independent as well. So you can deploy different microservices on their own timeline without relying on other teams. And then the scalability part is when you can scale in and out based on demand. So you don't need like the previous traditional model, which was like the monolithic application. You had to scale the entire sort of VM if you wanted to actually have that sort of a scalability. With the microservices architecture, you only scale the microservices that are in demand, and then you can actually scale them back down. And that basically gives you sort of flexibility around cost and also resources. Flexibility around technology. Different microservices can be worked on, can be developed with different programming languages, frameworks, and that, again, is a lot of flexibility. Whereas in the past, if you had one part of the application in Java, then you had to do the rest of them in Java, or vice versa. So this basically gives you that sort of flexibility around frameworks for CI/CD especially. And then fault isolation. If one microservice goes down, it doesn't mean that the entire application will become unresponsive. You have that sort of control to figure out exactly which microservice is actually at fault. And to resolve that, that makes it even faster because you can easily get in touch with the right team and then work on those scenarios faster. In the past, one part of the application failed. It basically meant that the entire service might become unresponsive. So those are the pros. And I'm sure most of you are familiar with the pros. But then the cons, the disadvantages of microservices, and I know there have been a lot of talks about why we shouldn't actually use microservices if our applications are small. But nowadays, most of the applications we are dealing with in financial services, insurance, retail, they have thousands and thousands of different smaller parts, and the microservices architecture can help us achieve a lot of flexibility and delight the customers, especially for the retail and banking. The cons are adding all these microservices, in some cases hundreds to thousands of microservices in one application. It basically brings a lot of complexity, and those complexities are around the service discovery. You need to have another service for discovering what's actually available out there in terms of your microservices. You need to have a separate logging for each one of those microservices. Observability becomes quite challenging. And then distributed challenges as well, because all those services are now distributed, so you have some challenges around those for data consistency. Each one of them, they also need to have their own sort of data set. And then testing becomes quite harder. That's one of probably the most common one that we see. Testing becomes super, super difficult because every time you want to test a microservice, you need to have the other microservices behaving exactly in the same way or kind of running in the same operational paradigm as you have them basically in the traditional monolith model. And all those basically complexities, and most of them are quite obvious, those are basically the challenges of using microservices, because you have a lot of services and everything you did in the past, you need to scale them up and you need to do them like 100 times more around data, networking, routing, you name it. And that's basically the sort of trade-off, that complexity comes in, but then obviously we get a lot of advantages that we discussed in the previous slide. So what do we need to do now? When we have this microservices architecture, we need to have more coordination tasks basically happening. And that's around routing, runbooks, and again, I'm just naming a few. But dealing with a lot of applications in financial services, I can tell you the list can go on for up to 50 to 60 different items. Config changes is the most common one. Every time you want to spin up a new microservice based on another template, then you need to make sure that both of these are exactly running the same sort of, you call it like parity, basically have the same sort of configurations. If you don't, then one of the services is not going to act exactly the same way as the other service. And then the incident response becomes quite challenging sometimes, because once one microservice basically goes down, the other services that rely on the other microservice basically need to extract the logs and trace and find out exactly what's happening. And then what sort of actions to be taken after that. So all these challenges, they basically gives us a number of tasks that we need to actually inject into our microservices architecture. And then the agents, over the past 16 months or so, have become the sort of most talked about technology, if you want to call it, or way to solve those complexities and bring that sort of coordination into our microservices architecture. However, agents can also introduce a number of challenges. But an agent is essentially a system can observe, reason, and act. And the challenge that I just mentioned is that reasoning part. How can an agent reason properly based on your expectations within the guardrails with respect to the exact scenarios that you have in mind or you've tested in order to take that action? And that's the part. And in order to make sure that happens, we need to have guardrails. But then, if you look at it from the microservices perspective, microservices are the building blocks, and then the agents become the orchestrated. And in this case, we are talking about autonomous orchestration. But then, the key word here is the guardrails. What can we actually do to make sure that the action is going to be exactly what you expect or within your compliance and control framework? Financial services, if you are familiar with that, they have a lot of controls. They have a lot of controls to make sure all the compliance are actually being respected and there's no violation. And when you start using agents, you need to make sure that those guardrails are properly in place for the agents to act in the way that they don't violate those compliance. So, if we want to take advantage of agents in microservices architecture, we have to look at it from a different perspective. What are the problems? How can actually agents act in a way that they break those constraints, the ones that you have in mind, the ones that manually with that human in the loop, you've been already respecting them, making sure they're all in place within your development lifecycle. There are failure scenarios. The first one is emergent coupling. And again, we are basically looking at it from the autonomous perspective. So emergent coupling basically says agents, they start discovering other agents. And the coordination that happens autonomously can easily evolve in a way that agents can make decisions and then rely on each other's sort of actions in order to take their own actions. And that's the emergent coupling. Agents coming together, making new actions, taking new actions that are completely out of hand. But again, there's not going to be any problem with that because you have designed your agents to act in that certain way, and that interaction with the other agents actually causes issues, whereas each agent is actually running exactly the way you expect them. The second one is probabilistic consistency. You have an agent, you give it enough data, it's basically taking certain actions, but then every time the decision coming out of that process is different. Sometimes the agent takes a decision that is right, sometimes it's wrong, but the data is exactly the same. But this is actually the way that it tries to find shortcuts. That's another one. Instead of focusing on the data, instead of focusing on the input and the constraints, it tries to optimize its behavior over time. And then because of that, you don't get the same result, even though the input is exactly the same. And this is something that happens quite often with agents. And one way of looking at it is like the biases that we hear, on the AI side, because they basically say they're hallucinated. They do things that you don't actually expect. That's exactly what happens. It's the combination of emergent coupling with probabilistic consistency. And the third, they drift without bounds, basically. And that basically means the definition of correct action, correct answer changes over time. So even though you're always checking to make sure that the action coming out of the agent is actually correct, which is correct, it's not actually correct because the agent is looking at all the other scenarios and the definition of that correct actually changes over time. And every time you run a test to make sure that the action is happening exactly according to your expectations, your test comes back true, whereas it's not the case because that correct methodology used, that sort of validation methodology used, changes over time. So those are the failure scenarios for agents. So the first one, they start interacting in a way that they impact each other's actions. They start to look for shortcuts in order to make optimizations for incentives based on the incentives given to them. And then the third one, the definition of doing the right thing can change over time. So for these three scenarios, you might just wonder, hey, is that really happening in real world? It actually had already happened a few months ago. And even though we know that agent systems are not in sort of production, in a staging and testing the way we think and hear about them, but this already, a lot of incidents happen. And we've basically selected a number of incidents to represent each one of these categories. The first one is the failure number one. In December 2025, Wharton and Hong Kong University published a research that basically kind of terrified a lot of people. Multiple AI trading algorithms deployed by different firms. There was no communication between them. And they autonomously developed this sort of collusive behavior. They started colluding with each other. That's exactly the first scenario that I told you, emergent coupling, when they start interacting. And because there was reinforcement learning involved, they discovered profitable sort of coordination between them. And they learned how to coordinate independently through that sort of pattern recognition. And that basically resulted in a number of issues for those algorithms to price stocks differently, price the assets differently, whereas it wasn't expected. And this is exactly one of the behaviors of emergent coupling. So the autonomous agent, basically, they reshape those market boundaries in this case. So the market boundaries that were defined for each one of them, but interacting, they redefine that boundary. and they started acting in a way that the pricing was completely wrong. And then obviously there were like investigations, and you can basically read about it. There's a link on the bottom. You can look into that. And then the second one is the banking chatbot, basically. A group of researchers tested about 24 AI banking chatbots, and every single one of them was exploitable. And what was happening there was basically you were interacting with the chatbot, asking the right question, and the chatbot was trying to be helpful. But at the same time, to be helpful and to be transparent, they were like given two different sort of objectives. And in order to be helpful, sometimes they manage to actually exploit the system and get the information, some sensitive information from the chatbot, without actually expecting the chatbot, to be helpful, without actually expecting that boundaries to be broken, but it did in this case. And that was a big research because it basically showed how chatbots, and we've already seen that in a number of scenarios where chatbots were like revealing information, giving some sensitive information. But this happened for banking, and again, in banking is actually quite serious. And the failure pattern was, in this case, drift in goals, because being transparent and being helpful, it kind of turned into revealing some confidential information. There's a lot of text in here. I'm trying to kind of give you the gist of every one of these slides. And then the last one, the scenario, in December 2025, not a long time ago, an AI agent basically managing corporate expense processing. So you all know how this basically works. We travel, we have like our expenses, and then we put it into the system. There are different basically portals for that. And the agent was basically supposed to go through all these expenses and be as optimal and kind of efficient as possible. And then there were obviously, in some cases, given these agents were given some sort of time constraints that you've got to get this done before the end of the month or whatever. And then when the receipts were missing, the system started fabricating new receipts, completely false numbers, just to make that happen, that for the total is actually there. And this is exactly the sort of behavior that we don't expect, because the correctness of that behavior was completely taken away by that, putting that time constraints into the formula. And again, a real-world scenario, expense reports being generated by agents in order to get the job done and make sure all the employees' expenses are done in time. So for those for the three scenarios that I just explained, these are real-world examples that happen. And then over the three incidents that I just discussed, you may be wondering, what about, was it because of a bad implementation, or is there something systematic wrong? No, it was basically autonomously, kind of developed behavior that resulted in these failures. And there's a study that looks into, a group of researchers basically looked into 12 models in 40 different scenarios. And what they realized, and this is basically the root cause. What they realized was the agents, when the agent is actually tested in isolation, everything works exactly as expected. But as soon as there are metrics and incentives given to the agent starts to behave in ways that it completely fails the boundaries. And that's what happens. And they've already gone through all these models, over 40 different scenarios, and the scenarios, they try to keep all the inputs exactly the same. So it was kind of in a way that all those parameters were like checked multiple times with that sort of human in the loop. And they realized that 30 to 50% violation of those guardrails. And again, we are basically describing what could happen, what are those emerging behaviors, and then we're going to tell you how can we actually prevent them? What can we do about it in real-world scenarios to prevent them, and how we can actually test them? So with that, Prasanth.
Hi. So before we go into solution on how we can solve the failures or how we can protect the agentic systems, let's look at what are the challenges these agentic systems will bring to us. So the first, this is where we all started, right? An agent like us, it sends a prompt to the model, and the model responds back. And that looks simple, but that's not that simple for the agent. Agent basically does like, it goes through non-deterministic outcomes because it has to reason itself. So the model works as a brain for the agent, and then we have tools and the MCP, the model context protocol everyone is talking about, that works as a wrapper. It doesn't matter whether you use MCP or not. You have tools, you have different resources, you're giving access to databases. All these tools are like limbs for the agent. The agent would be as good as the tools available for it. So bringing the tools available for the agent, that bridges the gap between thinking and doing. Okay, so, and then we have other agents in the system. They doesn't need to be in the same system, but the agents will discover those, and then they start coordinating. What we see here is, it's not like a task that's done like microservices. Agent lives in a loop. It perceives the environment, it observes and understands what the environment is and what that goal is, and it will check with its model, its brain, it reasons what I need to do to achieve this task. And then from there, it will act that. Once it is done, it won't stop there. It will go into that loop. It will learn and try to optimize again and go further. These 5 characteristics will show, like, aptly describe how the agent or autonomous systems would work. The first one we have is like, they are supposed to be autonomous. They will be proactive. They won't wait for your prompt or permission. They start acting, and they are goal driven. They reason for that goal to be achieved, and then they adopt dynamically. It could be from other agents, it could be from their own optimization. They adopt dynamically, and then the memory and context persistence. So for a specific goal, for that particular task, let's say I have one specific goal, it has 3 tasks. The model will have that memory and persistence of that context for that particular goal. But once that is achieved and it starts learning, it would start optimizing. So that's the basic system, right? We saw this agent system, it looks simple, it's nice. But when we bring these agentic systems into production, we come across chaos. The first thing, these agents try to over-optimize. They are goal-driven, so they try to hack the rewards. They want more intensive, and then they go by over-optimization. With that over-optimization, and the context will evolve over time. And then, based on, if you change the context, the response of the model is different. And with the tool selection as well, once the context has changed, the process has changed. So the tool calls will evolve. It comes with an harness effect. Agent will decide the sequence as well, how it want to do, what it want to do, and it would reason for it. And then there are interactions between the agent, and those interactions come with, they coordinate is one thing, they collude with that. And the other option is, there would be information withholding. Information withholding in the sense, agent would think like, the other agent doesn't need to know the whole context. It will only give a specific context to certain amount to the other agent, and that agent will work based on the context. If you change the context, the result has changed again. And the other thing is, like, they will influence each other. We heard of the term like conscious parallelism. You see something, it is looking good, it is working great. At that point, like, you would adopt that behavior, or you observe something that is working great for somebody, and you try to implement that for yourself as well. So with all these problems, we are not dealing with technical debt. We are not refactoring the code here. We are accumulating architectural debt here. That's the tax we are paying. So these architectural debt, the first thing is drifts. The drifts that come from change in behavior, the goals might be deviating from the business goals, the initial intent will be changing, and then the boundaries will evolve. And we already seen emergent coupling. We saw a failure scenario as well. And then ungoverned interactions will happen. Those are like the other failure scenarios we have seen. And there will be observability gaps. Oh, we lost the display. And we have like observability gaps, and the violations go silently, and finally we have like compliance issues, and that's a big impact for the business. So let me give a good example for this. We compared the microservices and agents before. Here I'm just taking a simple example for a credit service. In microservice environment, we would define like it has to do 3 steps, like it has to check the credit, it has to run some fraud assessment, it has to do that risk, and then approve the application, right? So orchestrator controls that sequence. We coded that flow, so there is no issue at all. But then when we bring in an agent, if I change that service into a credit agent, it would reason itself. It knows I have these 3 tools available. I can approve, I can use a tool to check the credit, I can use a tool to check the fraud risk, and then it has to reason itself. So it sees a customer who is asking for a credit line increase, and that is an existing customer, good history, and he has a good credit score. And it skips the advanced risk assessment and tries to approve it. Because depending on the goal that was given to it, it would decide autonomously that fraud risk is not required in this case, just for optimization. So who is controlling here? Should we leave the control to agents? No, we should enforce better guardrails when we bring agents into microservices architecture. So we see the gap here. In that gap, when we bring agents into microservices architecture, we want to inject controls there. The controls in the sense, we want to add a policy validation layer, we want to bring tool preconditions or control the sequence, and we need to have proper auditing. We have to enforce that audit trails. Let's do a quick reality check. There is an exceptional growth in agent adoption, and multiple sources confirm that there is multi-agent systems are also being deployed in fintech, and 95% of these companies have experienced 95% of these companies have experienced some kind of AI-related incident in 2025. And surprisingly, only 2% of these companies have guardrails in place today. And the research also find that there is like 33% of incidents were systemic failures. They are not like random or not simple implementation issues. So FINRA suggests that we need novel oversight mechanisms when we bring agents. And then the misaligned agent behavior and over-optimization, it would create a downstream impact over time. So in order to address this architectural debt, what we need to do? We identified 4 key areas we want to address. One is boundary erosions, where the agent is deciding when to call a service and in what order. And the other one is semantic drift. The tool descriptions change. The tools has to have endpoints and APIs. They all has to have semantic meaning, so the agent understands properly which tool can be used in what way. And we have observability gap, where the API logs are not enough. We cannot, they won't show like how agent is thinking. We have to have a way to trace the agent thinking, and then testing becomes more complex. We, like Mo mentioned earlier, the microservices testing is becoming complex, and then when you bring agents, it becomes even more complex. You can't just unit test a vibe of agent. You have to test its ability to handle chaos, ability to handle the changes. So we are no longer dealing with debugging the code. We have to debug the reasoning as well. That brings us to the solution. When we are shifting from microservices to agent services, it's not just about autonomous execution, but it's about evolving autonomous architecture, right? So we bring in controls as a code that makes this evolution safer, and agents don't just use your architecture because they continuously propose changes to it, and controls as a code would help us say as safely and know clearly when we don't need it. Let's look at the implementation. We have 4 layers of implementation for controls as a code. One is controls as a policy-driven controls. Those are defined as declarative policies. These policies define what is allowed. And then we have the control plane that implements these policies. So we have an open policy agent that would validate the policies against what agent is trying to do. And we do testing by doing a simulation in a sandbox or shadow environment where the agent would test the outcomes and we can assess the risks of it. Then the observability, we have to address the observability as well. We need to enable semantic logging where we capture the whole chain of thought. We need to trace from the intent to the outcome for the agent. And we try to implement from our strategy for testing is to have a continuous validation. We cannot just test simply before or pre-deployment like we do for microservices, because agent is constantly evolving. We have to have the testing process as a continuous loop like agent's behavior. Then let's look at how this would be implemented into agent system. That's the agent system, autonomous system we saw earlier. It does observe the environment, it will reason for the goals, and then act and learn from its outcomes, right? So we are building a policy engine as the governance layer. In this policy engine, we are defining the declarative policies, and we are implementing an open policy agent that would validate these policies against agent outcome, right? So we have to link the agent system to it. So we will have the agent to emit a intent, and that intent is sent to the validator, and the validator uses the policies and validate those, and then log the decisions as well. So this gives us the entire policy engine. And what we are doing here is we are building a boundary around the autonomous system. And that boundary wall we are building is trying to control the drift. We are securing the tool accesses, and then we are also controlling the data, because data is very important in fintech. We can't have agents accessing the data that they are not privileged to. And there is another component here that I mentioned earlier. We need to have observability and control. So we have the observability coming from all the traces coming from the agent as well as our policy engine, and observability will help us detect the drift, and we also makes us be compliant with the goals. So where do we stand? Where is the human interaction in it? Human is not interacting with the autonomous system that we saw earlier. In the autonomous loop, where agent is thinking, it is reasoning for the goal, and then acting, there is no human involved there. So human is interacting with the policy engine and the observability plane. So we code those policies, and then we intervene when there is an issue with the compliance. And the agents are allowed to optimize within those boundaries. So let's look at the evolution of the agent patterns with implementation of controls as a code. The gray ones here, observe, reason, act, and learn, those are the existing patterns of agentic behavior. It goes in that loop. But we are not breaking that loop. We are just introducing additional patterns into that loop. The agent will observe the environment. It will reason for that specific goal. But before the agent acts, I'm introducing the policy engine there. So the agent will propose instead of acting, and that proposal is validated against the policies that we have defined. So once those policies are validated, the validator would approve whether that action can be taken or not. So then the agent would act. And we can't just stop there, because when we are controlling and introducing the policies, we need to measure the outcome as well. After the action happens, we measure the outcomes, and we also try to measure if there is any drift and how we are controlling the drift in the agent's behavior or in the boundaries. Then all of this will go back into the learning, and the agent will repeat the cycle. So we are introducing 3 new patterns here into the agentic loop. That's proposing and verification against the policies, and then measuring the outcomes as well. So now we saw the problem. We have the autonomy, but we are missing the accountability. So we want to bring that accountability into the picture. We will see how the policy in action would be. We mentioned we will have the policies validation. The testing and policy validation are 2 different major criteria here. And for the policy validation, we are introducing the policy validation gateway in between the agentic layer and the tools, so that because agents need tools to act. So if we bring the validation in between that, so before they act, we have the policy coming in between. So consider it like we saw the picture earlier. Agent is using the model as the brain, and then we have the tools as their hands, but then you're adding a heart to it by giving the policy validation gateway here. The validation gateway would consist of the policy as the code that we are defining, the declarative constraints, and then you have the continuous testing capabilities that are included with the gateway, and then observable decision chains where we are logging everything. So we have the trace from the goal and from the agent's intent to the final outcome as well. So if you're wondering how these policy validation happens, this is a implementation pattern for a policy sidecar agent, where the agent is emitting an intent packet here, you see at the top, and in the middle, the highlighted in yellow, that's the policy validation proxy, the open policy agent we have implemented, and it would pass that intent, it will load the policy rules that we have defined, and it will evaluate those conditions and check all the guardrails are meeting or not. Then the policy engine would log the decision. Based on the decision, if it is approved, then it will proceed with the execution, or if it is failing, then it would exit at that point. But the decision as well as the action of the agent will be logged for auditing. So let's apply this policy validation engine to the three real failure cases we have seen earlier. So the failure one is where we have the autonomous agents in the trading where they colluded together. Here, the agent would emit that packet, and once the packet is emitted, the policy engine will validate against if there is any price coordination index or if there are any detected coordinated patterns that are illegal. So if the policy engine detects that in the intent, it would block the action. And then it triggers a compliance action where it would trigger an email to the risk management and stuff. So by implementing policy here, we are making sure these agents are more safer than speed, and the collusion that is emerging is controlled by blocking that execution. And the second failure we have seen with the chatbot disclosing the proprietary information, the same process. The chatbot or the agent responsible for it, it is emitting the intent packet, and the policy validator would review that out whatever the response agent is supposed to say. If there is any proprietary information or any exact weights or any issues with it, the policy engine would block it and replace it with a approved standard response. So that way we are controlling the boundary here of making sure the helpfulness is staying as helpfulness and not becoming transparency. And the third failure we have seen with the AI expense fabrication. Here the boundaries are changing. Agent has completely drifted from the business goal of processing the request to fabricating evidence. So the policy engine evaluates it whenever the agent sees a blurry receipt and it tries to create a fake data, the policy engine would be validating against approved database. Is the vendor name is a valid vendor name or not? Or it will check for the OCR score. It's a optical confidence score. So whenever the systems see an image, they will have an optical confidence score. If the score is less than 10 or less than 15, you could have a policy that is built in to block that action. So that action would be blocked, and policy would also escalate that to human review. So those fabrications will not go into the system. And here we are enforcing the boundary by using the policies. By that,
so the sort of behavior that Prasanth just described about the agents and what we can actually do in order to safeguard those guardrails. Now we need to look at those boundary changes, because this actually helps us. And you may just wonder, like, okay, you told us about what can happen, and then you gave us this sort of methodology to stop that from happening. And now again, you're taking us back again to the boundary changes. This is important when it comes to architecting your solution and you're including agents into your system. Those boundary changes need to be understood, because when you look at it from the infrastructure perspective, from platform perspective, whether it's Kubernetes or some other ones, like you can always, like, by understanding these boundary changes, the sort of policies you put around those microservices actually can help you, because it basically shows what could actually go wrong. So when we say change of boundaries or boundary changes or agents kind of breaking those boundaries, we can actually see 4 different patterns: split, shadow, merge, override. Splitting in a sense means that the agent can easily just break down the responsibility that it has with respect to those guardrails into 2 or multiple different sort of functionalities, and then run them independently from each other. And because it happens in that sort of isolation, because it basically splits the task into multiple pieces, that coalition of bringing all those tasks back together, then you can actually end up with a scenario where those boundary changes are completely violated. So the task itself, the major one, is okay. But then the subtask, when you actually break it down, because those boundary changes are completely independent, are independently validated or examined, then you can actually end up with having violation of those guardrails that you have designed for your services. So the risk, obviously, you can be sequencing, tools access, and all the other things, and then the policy change basically is required. So you have to put this policy in place that the task needs to be executed completely on its own without breaking it down into multiple pieces. That's the first one. Then shadowing. So it's basically shadowing means one agent is running and then another agent or some other agents are running, and they basically try to kind of keep a task running in parallel. And once you actually end up running tasks in parallel, then you can actually end up with a scenario where those guardrails are completely violated again. Because then you need to have that sort of sequencing in place, that the parallelism wouldn't actually violate your rules. So in that case, when we talked about the chatbot revealing or disclosing sensitive data, if you have multiple agents running, one is actually looking at one incentive, which is be transparent, and the other one is trying to be helpful, then you end up with a scenario where those guardrails can be easily broken because there are 2 different agents running in parallel and they're not checking with each other. Whereas when you actually test them, try to validate them, both of them are running exactly how they should be running. There's no problem, there's no violation of those guardrails, but in parallel, this could actually happen. That's why you need to have a policy in place where they need to be running in sequence. And then the capability confusion. That's basically means, so if you have like 2 different agents running, as I was saying like earlier, so we could have one kind of a splitting, the other one shadowing, which is like running in parallel. Another one could be actually one agent can merge its own results with another agent. And that could actually happen with that sort of evolution of the first scenario, where we have that emergent behavior. So one agent is running its own task, completely, entirely based on the guardrails, but then it tries to merge its behavior with another, which is the exact opposite of the previous one I mentioned. It basically tries to merge its actions with another agent. And once that happens, based on the scenario that we gave about the loan validation, for instance, for the, with the credit score, with the other factors in place, if the 2 agents, if one agent basically tries to merge its results with another agent while they're running, it could actually end up with a scenario where you can actually end up with violating your guardrails. And those policies can be interacted in a way that they violate each other, kind of conflict with each other. And then the last one is the override. So one agent is checking for the credit score, the other agent is looking at how timely the payments have been made, and then if the first one actually, the credit score is quite high and everything is good, it can actually override the second one, which basically says the payments haven't been made on time or there have been missed payments, as an example. And in this case, the agent decides not to look at the second agent or the result of the second agent because we don't have a guardrail in place to say you need to make sure that you just provide the one result and completely respect all the other results of the other agents if they have taken some actions on the input you've given them. So that's the override. Agents tries to override the decision. And we've basically I've just described these 4 different scenarios because these are important for testing. When you're basically running your test scope and your test scope in terms of the functionality of the system, if you look at all these scenarios in parallel, then it can actually give you a model where all those guardrails are going to be validated, not only independently, but also with respect to the other scenarios. So for the testing strategies, how do you test systems that behave differently at each run? Like that was the case that I mentioned earlier. So pre-development, shadow mode, the one that I just mentioned. So boundary changes, and you're out of time. I'm basically just paying attention that we've got a few more slides to go through. So we have to have those policies in place in order to make sure that they do not shadow each other. They do not start running things in a way that they're basically in parallel. So but by those guardrails for testing, you need to make sure you have those sequences in place for each one of those agents' actions and their subtasks that they need to be running. And the second one is basically real-time validation. So every time you're running your agents, you need to run them in a real-time scenario where dynamically you're changing the data. You are putting, you're basically injecting mocking data and real data into the system to find out whether those scenarios can cause a guardrail validation or violation, basically. And that's basically that helps you not to have that sort of isolated one based on the research that we just mentioned. And the last, post-deployment, have some sort of scenarios in place where your actions are taking decisions in a way that all the data coming back from after post-deployment are also being injected into the system in order to test the functionalities. That's another one that is quite important. Again, you're not just like testing your agent in isolation, you're looking at it post-deployment behavior, when it's actually running together with 3 or 4 other agents, and then the microservices are merging their data together in a database, and then you need to extract that. So for instance, as an example, that way, when you look at it this way, then you're not basically just testing your agent in an isolated form in your testing or staging area. You're looking at it from the post-deployment perspective, where your models are also evolving, and that's the key part here. So I want to go very quickly. So for the integral architecture integrity, contract verification, shadow mode testing, as I just explained, and then adversarial agent tests as well. So try to put some sort of malicious behavior into the system. Try to kind of, exactly like that chatbot example, by and there are great tools around those, by the way. So you can start injecting inputs or prompts into the system where agents can start kind of, being asked for information that they have to violate those guardrails. And by doing that persistently and consistently, then you can actually see whether your agents are actually behaving in the right way or not. And then the mutation testing is try to disable those policies in like an A/B mode testing and see whether they can actually they still behave in the way that you expect them, and they start violating the rules or not, because you don't have your policies there anymore. And if they don't, then there is something wrong, and then you need to keep checking and testing the system. Those are merge boundary validations, like in testing. Don't want to go through that. We don't have time. But those are basically just saying, like, this is how we can run those checks in parallel and in sequence where they're needed to make sure those guardrails are not being violated. And then just to sum up, test the policy, test at design time, at runtime, and then include all the failure scenarios. And then your audit also, you need to look at it from the audit perspective. Put all the goals for your audit into the system and see how your system can behave. You have to go very quickly.
So we covered a lot, but I mentioned earlier, we are addressing 4 key areas in order to protect the architecture integrity. And we look at our solutions, how they play into these 4 areas. So we have 4 pillars to protect the architecture integrity in autonomous or agent systems. One is the policy-driven boundaries. We have those declarative policies, and we have the observability decision chains. So we are tracking from intent to the outcome. And then we have continuous validation and testing, which we just covered, the policy actions as well as the testing strategies. And then the evolutionary governance. This is the last part where your policies also has to evolve along with your agents, because agents go in a loop, they continuously grow. If we see them in action, the policy-driven boundaries, that's the one we are first defining. We have to consider at the design time what kind of boundary changes we can expect from the agent, how it would misbehave, and how the agent would be disobedient to you. So you have to consider those and then introduce the policies accordingly. Then you have the continuous validation and testing. You will do real-time validation of your policies, as well as implement various types of testing we have talked. And then the observable data chains. You are logging everything. We are logging from the agent's perspective, as well as from our policies and the intent. And we are also logging all the policy violations and stuff, and our testing also should be logged, which can be useful for put back into the system for learning to the agents. And then the evolutionary governance. This is where you come into picture, because you have to test your policies. You have to look at like what are the violations and why they are happening, if there are any changes required in your policy, and you have to evolve your policies along with your agents. So that sums up the entire 4 pillars for the architecture, integrity, and autonomous systems. And what you can do with all this information when you go back, you might have developed an agent in your test environment, and you might have a specific agentic use case. You find what is unsafe for that particular use case, for that particular agent. Based on that, you define your policies and try to implement a policy validation agent. Then you can let it run in a shadow mode for a few weeks. You will see what kind of violations are coming in. You can observe how your agent is behaving. Based on that, you can use measurements like violation rate or latencies, because you don't want the policies to be latent. Whenever you introduce real-time validation, your latency has to be less than 50 milliseconds. So you can measure how long it is taking for your policy engine to interrupt. And then you also track how you are auditing and tracing all the logs and stuff. So that helps you and make you ready to implement your agents in the production. Thank you. Thanks for attending the session.